Welcome back to this course on multicore systems. In this lesson, I will give a definition of what a parallel computer is, present Flynn's taxonomy of computer systems, and discuss two classes of shared memory multiprocessors. Now that we know the reasons for the transition to multicore designs, let's try to define what a multicore, or more general, a parallel computer is. Here's a definition given by Almasi and Gottlieb already in 1989. A parallel computer is a collection of processing elements, called cores in the multicore era, that cooperate and communicate to solve large problems fast. Almost all computers are connected by the internet. Does that make them a parallel computer? Not really, as they generally don't cooperate and communicate to solve a large problem. In general, a parallel architecture therefore consists of a computing part and a communication part. The computing model defines how the cores or processing elements are organized and how data is processed. The communication model defines how they communicate. Let's talk about the communication model a little bit more. In general, two communication models can be distinguished. The first is to communicate via shared memory or shared address space. In this model, the cores communicate using normal and stores that we know from the uniprocessor case. In this model, explicit synchronization is required because the receiving core needs to know when the store has happened. To give an example, this figure here shows two cores or processors, P1 and P2, and the memory both can access, and is therefore called shared memory. Often I will use the terms core and processor interchangeably, even though it is not 100% correct. Nowadays, a processor is called a single chip that can contain multiple cores. So in order to communicate data from processor 1 to processor 2, processor 1 first has to store the data to shared memory, and thereafter, processor 2 can load the data from memory. The second communication model is message passing. In this model, cores communicate by sending and receiving messages between them. In this case, synchronization is implicit because when the receive has happened, we also know that the send has happened. To give an example, here again we have two processors, but now the shared memory has been replaced by an arbitrary communication network. To communicate data from P1 to P2, P1 has to send a message through the communication network to P2, and P2 has to explicitly receive it. There has been a lot of debate about which communication model is better. I have worked on both and can add a lot to the debate, but again, in the interest of time, I will not. In a very small nutshell, if the application to parallelize is rather static, such as matrix multiplication or Gaussian elimination or the like, then message passing may be just as easy or difficult, depending on how you look at it, as shared memory programming. However, if the application is highly dynamic and you don't know beforehand which core is going to perform which parallel task, then shared memory programming is considered much easier, and I tend to agree with that. For this reason, in this course, I will focus on shared memory architectures. Another classification, or taxonomy, is the one due to Michael Flynn. He classified parallel computers by whether there are single or multiple instruction streams and whether there are single or multiple data streams. So every computer can be classified as an element from the Cartesian product of single instruction, multiple instruction, and single data, multiple data. If there is a single instruction and a single data stream, then the processor is classified as SISD. SISD processes are the conventional uniprocessors. It may be argued that superscalar processors also execute multiple instructions in parallel, but in personal communication, Michael Flynn said he meant the programmer's perspective. Surely, from the programmer's view, superscalars are SISD. The next class are the single instruction, multiple data, or SIMD or SIMD processes. They always execute the same instruction, but on different data elements in parallel, so there is a single program counter. Vector processes, for example, belong to this class, and so do the short vector SIMD ISA extensions we discussed in the previous lessons, but also the connection machine CM2, which had up to 8K very simple 1-bit processing elements, belong to this class. Next, in the third row and the second column is the multiple instruction single data class. There are no processors that really belong to this class, and therefore it can be considered an anomaly of this classification. Finally, in the bottom row and the last column, we have the multiple instruction, multiple data, or MIMD processors. Most parallel processors belong to this class and are used in clusters, SMP servers, etc., etc., etc. To visualize these classes, this slide shows figures that can be found on Wikipedia. Very briefly, because I do not want to repeat myself, a SISD processor or SISD processor has a single instruction pool and a single data pool. An SIMD processor has a single instruction pool but performs a single instruction on multiple elements from the data pool. A MISD processor performs the same instruction on multiple elements from the data pool, and a MIMD processor simultaneously executes different instructions on multiple elements from the data pool. A few slides ago, we saw that parallel computers can communicate via shared memory or via a communication network. Even shared memory systems, shared memory processors, can be subdivided into two classes. The first, shown here in the third column, are called symmetric multiprocessors or SMP, and the second is called distributed shared memory or DSM. In both cases, there is a single address space, so processors can communicate using regular loads and stores. They differ, however, in the physical organization of the shared memory. In an SMP, illustrated here, there is a single centralized memory as shown here. This also explains the term symmetric, since the memory is symmetric to all processes. For this reason, SMPs are also called Uniform Memory Access or UMA architectures, since the memory access time is uniform independent of which memory location is accessed. Distributed shared memory systems, on the other hand, have a physically distributed memory organization as shown here. In this organization, each processor is directly attached to a local memory module, and the aggregate of all local memories form the shared memory space. However, a local memory access is much faster than a remote memory access, and for this reason, distributed shared memory systems are also called non-uniform memory access or NUMA architectures. This slide shows again the basic structure of an SMP. There are a number of processors, in this case 4, that are directly connected to one or more levels of cache. These are private caches, meaning that they can only be accessed by the processor or core directly connected to them. Furthermore, For reasons I will explain later, the processes are typically connected by a bus or some other broadcast-based interconnect. The main problem of this organization is that it has a centralized shared memory, which becomes a bottleneck when the number of cores increases. To alleviate this bottleneck, designers have provided a large shared cache between the interconnect and the memory, and experience has shown that it can support up to 4 to 8 cores, but unfortunately not much more. Large multiprocessor systems, on the other hand, typically use a physically distributed memory, as shown here. Each processor is now connected to a local memory module, and all local memories together form the shared address space. The aggregate of a processor, its private cache hierarchy, and its local memory is often called a node. Furthermore, the bus has been replaced by a general, more scalable interconnect that can provide much higher bandwidth than a bus. The physically distributed memory scales much better than a central memory. In addition, accesses to local memory are much faster than accesses to remote memory. So if an application mainly accesses its local memory, the average latency will be reduced. A disadvantage of this organization is, however, that communicating data between processes is more complex than it is in SMPs. This concludes this lesson. Thank you for watching. In the next lesson, I will discuss 2 challenges of parallel processing: limited parallelism and the relatively high cost of communication. Stay tuned.